I was wondering, if you could keep it.
Hello once again, Algebra 2 students. Mr. Record here, broadcasting live from Avon High School with my awesome Period 6 ACE College Algebra class. Well, half of my awesome college algebra class because we are still on I-Step day 29 and we've lost my sophomores today. But hey, our freshmen are going to hold the fort down because that's what they do, right? So in this section, 15.3, especially for those of you watching outside, we are going to investigate one of our final properties of logarithms. It's one that's called the inverse property, and it's just going to open the door wider for us to manipulate special logarithms that we see so that we can solve equations, apply them to science, and do all sorts of fun things with them. So obviously our objective, as always, is written above, and that is to solve exponential and logarithmic equations using the inverse properties of logs and exponents. So for our example 1, we are going to start by being super lazy and use calculators. How cool is that? So it says to use your calculator to find the value of each of the following expressions. And to be honest, there's really 4 of them that I want to work through with you. I want to work through the top row, A, B, C, and D. So we're going to take 5, and we're going to, what? We're going to raise it to a power that has a logarithm in it? That's kind of weird, right? We're going to raise it to the log base 5 of the value 3. And we're going to let the, like I said, the calculator do all the work. So I'm going to clear this out. Now I'm going to do this 2 different ways. I am going to use a TI Inspire here, which has the functionality that allows you to type in a log of any base. So for this particular calculator, that would be second 10 to the x. But before I do that, though, I have to insert the base, which is already, whoops, sorry about that. I have to insert the base, which is 5. Now I'm going to raise that to a power, and this is where I put that logarithm in. So I have second 10 to the x to get my log base 5 in this case, and I'm going to throw 3 in the argument. So if we look at this, we may not anticipate what the answer is going to be. Maybe we have an idea, but I'm going to hit enter, and interesting, it looks like I got 3. Now, is that just a coincidence? For example, what if I stay with this problem? Those of you that are watching, you can just kind of sit tight. What if I make this number a 27? 5 raised to the log base 5 of 27. What do you think this answer is going to be? 27. So I think we can come to the conclusion that if you have a base raised to a log of the same base, those things sort of, I don't want to say cancel each other, but they sort of kind of disintegrate, and the argument after the logarithm is going to be your final answer. Okay, and it's real simple. That's exactly what we're going to do. Now, for those of you, unfortunately, who may not have had a calculator that has the really cool log base whatever feature, in this particular problem, you might have to take 5 and raise that to, and then you'll have to put a special fraction in there. And if you don't have a fraction template, after the exponent, you're going to have to put parentheses with a division symbol within that parenthesis. But you have a log button that you could say the log base 10 of 3, right? I'm going to use the argument as the numerator, and then the denominator would be the log base 10 of 5. So you see how I'm going back up here using these ideas. Now, if this formula here is bothersome to you, you might want to go back and watch one of my earlier videos where I explained how this is developed. But in any event, if that's what we end up doing, we can see that the answer is going to be 3 as well. All right, so we might be able to cut this a little short. This answer is 3. What do you think the answer to E is? It is 9. 2 raised to the log base 2. Okay, now if we look at B, we've done something a little different here. Now we're going to take the log base 4 of a value of the same base as our logarithm, and then that number is raised to the 7th. So if we let the calculator do the work here, I would have the log base 4 of 4 raised to the 7th. And the answer is 7. If you're using a calculator that only has a log base 10 key, you would say the log base 10 of 4 to the 7th, because this is the argument of the logarithm, and that would be placed on top of the log base 10 of 4, which is the base that we were dealing with. And this should be 7 as well, and it is. What do you think the answer to F is? 3 over 2. Because these two guys, the 5s, match. Okay, now, does the same thing work for natural logarithms? Of course it does. We have to understand that this natural log right here has a base of e built in. So if you want to see the proof of this, I can go in and I can type a natural log and then take e to the 3rd power, and we will see that that's equal to 3. So this is 3. You can probably guess that this is 4. And the answers to G and H are 0.005 and 5 over 4, respectively. So the inverse property is very, very simple. And the idea behind it is just that logarithms and exponentials are inverses of each other, and they will sort of eliminate each other. Okay, so based on our observations in the above calculations, we can make a conjecture of how to complete this property, and we're just going to do more than that. We're going to just flat out answer it. The log base b of b to the n is n, or the natural log of e to the n is n. I'm not going to worry about the explanation at this point in the video. And then down here, if we have a base of b raised to the log of the same base, we get the argument, whether it's a logarithm of base b or a logarithm of base e. Ooh, that rhymes. All right, so, how do these things tend to work? Well, very, very often you guys might be working through a math problem and you come across a term that might look like any one of these 4 things. And we want to make these things as uncomplicated as possible so that we can move right on and continue solving. So if anyone were to ever encounter the natural log of e raised to the 3x, what's the answer? And you're okay to shout it out if you guys want to. You'll be on live TV or YouTube. It's 3x. Does everyone agree with that? Hopefully those of you watching can see that. The ln of the e sort of kind of eliminate each other. All right, now this one's a little tricky. For part B, I would advise you to rewrite the cube root of e squared so that it has just a single exponent attached to the e. And that exponent, would it be 2/3 or 3/2? Good, I heard one of you say it. It is 2/3. That's really important that we get that correct, because whatever that exponent is our answer. Because the ln and the e sort of kind of wipe each other out. Another way to think about this. Did we talk about a property the other day, you guys, that allowed the exponent of a logarithm to come out in front? I think we alluded to it, but I think that's something that we're going to still be discussing. So another way to think about this is to do that, and this natural log of e is going to be 1. I can prove that to you by just typing it in here and saying, hey, if we ever see the natural log of e, or e to the 1st, that's going to be equivalent to 1. So the coefficient that's out in front is all that's going to be left. All right, with this guy here, you got to be careful because the 2 is in front of the logarithm, and we don't want that. So we have to change this 2, so he is now the exponent of the x, right? Again, remember us talking about that? Now, this log has a base 10 that matches the base that's here, so we can basically remove them, and we have x squared. Okay. Now keep in mind, this trick only works if the bases are the same. For example, heaven forbid you saw something like this. oh man, if we saw something like that, we're in trouble, right? That thing's not going to reduce nearly as easily, right? It's so vitally important that these two things, these two bases, are the same number. And then it's also important that you don't have anything in front of the logarithm. So make sure that all of those exponents are moved as the powers. All right, and if we take a look at or part D, sorry, very similar situation here. This 2 is just not going to work for us, you guys. This 2 is going to have to plant itself as the power of the argument of the logarithm. So we have the natural log of x plus 1 quantity squared. The e and the ln will cancel, and then our result is x plus 1 quantity squared. All right. Okay, there are a few other problems in this group that I tell you what, I am going to go ahead and pause the video, and I'm going to go ahead and work these out and allow you guys to check them here in just a moment. And we're back. Hopefully, you had some success with those last 4 examples in example number 2, E, F, G, and H. E was pretty straightforward. The e and the ln will cancel, leaving you with the exponent x plus 2. But choice F was a little trickier. During the pause, the students that are currently in my class, we had a good discussion about how we would tackle this. So they're going to hear it again while I explain it to anyone watching. This is a little different. Because the ln of x plus 2 isn't sort of wrapped up, the x plus 2, excuse me, isn't wrapped up all together, we have to treat this as 2 separate pieces. And basically, we're just using a property that says if you have a base a to some power n multiplied by the same base to some power n, we learned a couple of sections ago that we can add those exponents. All that we're doing in this problem is moving in the opposite direction. We're taking a sum of 2 exponents and writing it as a product, of 2 like bases. At that point, the e to the ln of x is, of course, going to be the x, and this e squared just drops straight down. Okay? Something very similar is going to happen in G. We're going to split this apart as 2 bases of 5. Once we do that, the 5 to the log base 5x becomes our x, and then the 5 squared can become 25. H is a little bit more traditional in that each of these 2 logarithmic expressions are just going to simplify separately to give us the exponent 3x plus the exponent of 3. All right. Now, we move on to the process for solving an exponential and logarithmic equation. It's very, very similar. So what we've got right here is an example to the right. 3 plus 2 raised to the 3 minus 2x, all equal to 11. Lots going on with that. There's a lot of stuff in there. You're not used to solving equations that have x's in the exponent. That's why we are giving this its whole sort of chapter devoted to the process. So, and here it says if an exponential equation has only one exponential expression. Well, what I want to do is kind of focus more on the solution box for this, and then if we need to fill out the boxes to the left, we can go back and do that, but I'm more concerned with this right side. So what are we going to do with this first? Well, anytime that you have an exponent that contains a variable, any other terms that aren't like that, you want to get rid of them to the other side of the equation. So we are going to go ahead and subtract 3 from both sides. So that would give us 2 raised to the 3 minus 2x power, equivalent to what? 8? Now, here's the thing about the solution to this problem. We don't need logarithms, right? Hopefully we understand that we don't need logarithms. But I'm going to go ahead and kind of throw in this statement. If we use logs, if we use logarithms, what would the solution look like? Well, we could go ahead and take the log base whatever we want of both sides. The problem is we have to make sure that we use the same base. Seeing as that this is a base of 2, what base do you think we're going to use? Probably base 2. So we just rewrite the left side of the equation, and then we do the same thing on the right side, like such. Now, on the left side, we see that we have a log base 2 with a base of 2, so that means that these things are going to cancel each other out, aren't they? And we would be left with whatever the exponent was, in this case 3 minus 2x. Okay, now, does anybody know what the log base 2 of 8 is? What power do you raise 2 to get 8? The answer is 3, yeah. And now, you are free of logarithms, you're free of exponents that contain variables, so you can solve this fairly easy by subtracting 3 from both sides. And then, what? We end up with x equals 0? Wow, I didn't see that coming. But it's an answer, so we don't want to dismiss it. And that's certainly acceptable. I mean, that's what we could do if we want to use logs. Now, what if we don't want to use logs? What if we say, otherwise? Meaning no logs allowed. If you go back to this step here, is there a method that we talked about in a previous unit that would allow you to solve this? Is there something that you can do to maybe the right side, that 8, and change it so that it looks a little bit more like the left side? Change the base. Exactly. You could look at that right side, 8, and change it to 2 cubed. And if you do that, then you can just set the exponents equal to each other. And boy, that step looks awfully familiar because that's exactly what we had right here, isn't it? And then you're going to get x equals 0 in a couple of steps. So I'm not going to judge, what method should you use. You use what method you want to use to get a correct answer. Okay? You're going to come across some problems, though, that won't allow you to have that base that's going to match, and you're going to end up having to solve those most likely by using a calculator and a log button. All right? So let's go ahead and look at our example 3 here. We've got two problems here on this page, and when we flip the page, looks like there are 4 more. So tell you what, my intention with you guys is to do 2 of these. I would like to do, you know what? I'm going to change my mind. I'm going to do 3 of these with you. We're going to do A, B, and E together. And then I'll pause the video and then show you the solutions to C, D, and F. So if we go back and we look at A, 3e raised to the 2x plus 1 equals 12. How would we solve for that? Well, that's a great question, right? Well, it says solve each of the following exponential equations, and it says round your answers to 3 places if necessary. So that sort of opens the door that if we have to use the calculator, then so be it. So the first thing that we'd want to do with this is to divide both sides by 3, because that's going to get a number away from the left side and allow us to slowly but surely get closer to that variable x. All right. Now, remember what we want to do here. We would like for this exponent to become free and no longer be up here as a power of e. The only way that we can do that is to take some natural log of this expression so that the natural log and the base would cancel, right? I think I may have given it away. Which log do we use? We use the natural log because this is a base e. Had this been base 5, we'd have used the log base 5. So if we take the natural log of both sides of the equation, basically we're performing the same operation to both sides. What happens is that the ln and the e go away. We get 2x plus 1 equivalent to the natural log of 4. Now the problem is that we have no way to find the natural log of 4. That is an ugly number. So we would go to the calculator and we would compute the natural log of 4. Everybody's got a means by which to do that. You have a LN button on your scientific calculator. That's easy to find. And we get 1.386. It says to round to 3 places, so we can just call that 1.386 right now. So then 2x plus 1 is equivalent to 1.386. And now we got a very easy equation to solve. We're going to subtract 1 over, and then 2x would equal 0.386. And then just about out of room here, so one last step, we're going to divide by 2. Now, since we've already used the calculator to do some dividing, I don't see any reason why we could stop. So if we want to take that into our calculator and get 0.193, there's nothing wrong with that. All right. Now, the mathematician in me wants to erase this equal and put an approximately because I have rounded this answer. I'm not going to scrutinize whether you use an equal or an approximately, guys. All right, but that's what you're going to do to that particular problem. All right, let's go to B. On this problem, to get at this x exponent, we're first of all going to have to subtract 4 from both sides. To do that, we'd end up getting a 6 on the right side. Now, if you look at this, you're not going to be able to change the base. 2 and 6 are not very cooperative with each other. So what we're going to have to do is use some kind of a logarithm. Now, here's the funny part. What logarithm in what base would you want to use on both sides? What's the easiest one? Probably base 2, right? Because if you use log base 2, that's going to cause everything to cancel away except the exponent on the left side. And then the right side, we have log base 2 of 6. All right? Now, I want to tell you something. There's no wrong answer for that. You can take the log of both sides in any base that you want. You're just going to have to work a little bit more if you choose a base other than 2. And this is something that I'm going to talk about as we move into this a little bit more on Monday, you guys. But the log base 2 and 2 are going to cancel, and we're left with 3 minus x. And then the log base 2 of 6, that's probably something pretty ugly. Can you imagine? Like, what power do you raise 2 to get 6? So we go to our calculator, and however you have to figure it out, whether you use the quotient of 2 bases of 10, or if you do what I'm doing, you're going to get 2.58. I'll tell you what, let's round that to 2.585. And now, if we add x to the right, we would subtract 2.585 from 3, and I think we get what? 0.415. I'll let you guys verify that, but I think that's correct. You could also use that calculator if you had to there. All right, and again, technically this is an approximation. Okay? Let's do one more problem. There's one very special one that I chose here. E has got something very, very different going on with it. Something extremely different going on. Anybody recognize how we can handle this trinomial expression? In other words, is it possible that this thing has a brother in the math world that looks like this? Or a cousin? Did you know that? Did you know math expressions are related sometimes? They have cousins, and aunts, and uncles, and nephews. All right. Do you guys see where I'm going with this? This factors, doesn't it? Factors pretty easily. What does that factor into? X minus 5, x plus 1. Pretty easy to solve. You can do the same thing with this expression down here. We'll break it into 2 binomials where the e to the 2x is just a matter of taking e to the 1x times e to the 1x, right? That's going to make e to the 2x when we multiply them. Now, to multiply two things together to get 5, I bet we're going to use 5 and 1, since 5 is a prime number. And seeing as how this middle term here is negative, why don't we put the minus with the 5 and the plus with the 1? Do you think that would work? I think that would work perfectly. And now you use the zero product property that just says set each of these expressions equal to 0. So then we solve by adding 5 over to the right, and we see that this thing can be solved if we take the natural log of both sides, since the base is e. X pops out in front. Ln of e is just 1, right? I think I've shown you that a moment ago. And the answer is x equal ln of 5. Now, honestly, you could leave it like that, but if you wanted to figure out, okay, what is a decimal for ln of 5, since the directions say we're allowed to round to 3 places, 1.609 would work. But normally when you get into more advanced math, you guys, I'm happy if you just leave it like ln of 5. Now, this next guy is very different. Anybody out there can holler out what the solution to this is? I heard it. You guys are awesome. I heard my students say no solution. And that's exactly right. Yeah, maybe I underestimated you. See, if you try to take the natural log of both sides, some bad things are going to happen, like right here, like what in the world, right? We can't take the natural log of -1. Want to see me try? I think I did this the other day. I tried. Calculator doesn't like it. So if you ever come across an e to a power equaling a negative number, that's going to be no solution. So that means the only answer is going to be this natural log of 5 or the 1.609. Right? Now, what I'm going to do is I'm going to pick up in another video where I will go ahead and show the results of these 3 problems, and I will move on to the solutions of the problems in example 4 that just take the difficulty up a notch. So hopefully this has helped out, and I'll see you next time.